Okay, we started our new recording. How did we get a universe so big with so much stuff in it? Well, we started small. We started, we started, we started in a finite amount of space, and we got a finite number of these God particle ones. Now we define a God particle one. A God particle one is the smallest particle of mass. It has some elasticity and it's gaseous. Okay, and from that smallest particle, then they combined as positive GP1, God particle 1, ether pressure developed in our universe of finite volume. So once she gets a little bit of spin, then every part of the universe is going to move a little bit. Okay? And then because these things are elastic, they're going to bounce. They're going to bounce off of each other. Okay? And then the bounce may develop into a spin. And if it develops into a spin, it's going to spin other stuff. Well, what that bounce and what that spin did in a finite volume is it created a pressure. And as those God particle ones bumped to each other, eventually some of them stuck. Okay, they got stuck and they developed a strand. Now the strand is gaseous also. Has gaseous properties. The strand has gaseous properties. And then as time went on, the strand ones combined into bigger strands. And those strands eventually got woven into sacs. And the smallest sacs that we know of and can have mechanisms with which to view is the electron neutrino. The electron neutrino is about 1/1,000,000th the size of an electron. It has a tiny bit of mass, okay? Now, if you think of the electron and nucleons, if you think of them as woven sacs, okay? And they're mass energy vessels, okay? They transport both mass and energy. We know that because if you rip one of those sacs apart, the easiest way to rip a nucleon sac apart, or an electron sac apart, or a neutrino sac, the easiest way to rip it apart is with an antiparticle. Okay? So, what is an antiparticle? Okay? A positron is identical to an electron. Okay? But they both have a north pole, a magnetic north pole. The spin gives them a magnetic north pole, and it gives them a magnetic south pole. Okay? Now, when you look down on the magnetic north pole, when you look down on the electron, it spins clockwise. Then, when you look down on the north pole of the positron, it spins counterclockwise. That difference in spin is what causes the positrons to be attracted to the electrons. And they get closer together and their sacs get ripped apart. And once you put a hole in the sac, then the frequency of the expulsions and impulsions increases. And that energy is released very quickly. Okay? For a positron and electron, it releases a frequency of energy of 511 kilovolts. Okay, it's a very tiny amount of energy. But when you have trillions and trillions and quadrillions of these in the center of our galaxy near Sagittarius A, our supermassive black hole, with 4.1 million solar masses of neutronium. Okay. Now, there's nothing magical about a black hole. If you get more than about 2.16 solar masses of neutronium, which is what makes up a neutron star, if you get more than that, then light waves, instead of propagating outwards, propagate inwards from the event horizon. It has to do with how fast our ether particles are absorbed into the neutronium. Okay, the more neutronium you have, the faster it heats up, and the faster it absorbs energy and particles from the from space. Okay, and that absorption of ether particles makes space contract, and the contraction of space creates gravity as the ether particles flow in to the neutronium. As they flow into the neutronium and warm up the neutronium, as they flow into the neutronium and they decrease the surrounding pressure. So you have higher pressure the farther you go from a black hole. Now, at the event horizon, the pressure is so low that the ether particles cannot bounce and form a wave. I'm losing my voice, so we'll take it up next time. We'll see if we can download these videos on our computer. Talk more a different time when my voice is better. Bye.